You know, in our world, in wireless tech, there are these invisible forces. They literally decide if a signal lives or dies. And the biggest one? Radio frequency propagation. Look, for any of us in the RF game, getting a handle on this isn't just a nice to have, it's everything. It's the core of what we do.
Now, what we're about to walk through is based on some fantastic material. It's from a technical tutorial for RF techs and engineers, put together by the pros at RFI Detectives who are part of Virtualization Options LLC. And just so you know, this is part 5 of a 20-part series where we're digging into their report. We've basically boiled down their core philosophy into a briefing that's all about what you actually need to know out in the field.
All right, let's jump right into the big problem, the fundamental challenge we all face. What really happens to a signal on its journey? You know, from the second it blasts off the transmitter to the moment it, hopefully, gets picked up by the receiver.
And that's really the heart of it, right? That journey. RF propagation, it's just the study of how these electromagnetic waves make their way from point A to point B. It's all about figuring out how they navigate through, well, all the chaos of the real world. And here's the thing. That journey is almost never simple. I mean, think about it. If signals just shot out in a perfectly straight line like a laser in a vacuum, our jobs would be a piece of cake. But that's not how it works, not even close. The environment is always getting in the way, messing with the signal, changing its path, changing everything about it.
So what kind of messing with are we talking about? Well, a radio wave can do all sorts of things. It can bend, literally wrap around the curve of the Earth. It can bounce off stuff like the ionosphere way up there, or just a big building next door. It can get scattered by things like rain or even a bunch of trees. And, of course, it can just get straight up absorbed by an obstacle and disappear. And our job, our whole job, is to figure out how to predict and deal with all of that.
But okay, it's not all doom and gloom. We're not just victims of physics here. We have tools, right? We can actually impose some order on all this chaos. And one of the biggest tools in our toolkit is polarization. This is where we get to be engineers. We stop just reacting to the world and start actively designing a solution.
So what exactly is polarization? In the simplest terms, it's about the orientation of the wave's electric field. A good way to think about it is like controlling the angle of the wave as it flies through the air. Is it wiggling up and down? That's vertical. Side to side? Horizontal. You could even be spinning in a circle. That's what we're talking about.
And here's why that's so incredibly powerful. Think about all the things we can't control, like solar flares or the weather. Polarization is different. It's something we can set, right at the antenna. It's one of the few properties of that wave that we are completely in charge of. And by choosing how we launch it, we're giving that signal a huge advantage before it even starts its journey.
Okay, so that naturally leads to the big question, right? The so what? Why do we obsess over this stuff? Why is it so critical to, say, match the polarization of your transmit and receive antennas out there in the real world? What's the payoff?
Well, the payoff is huge. When you nail the polarization, you get a stronger link, period. You can dramatically cut down on interference because you can design your receiver to ignore signals that have the wrong polarization. It helps fight back against all that environmental muck we talked about. And you can even do clever things like frequency reuse, packing more data into the same channel. It's not just theory, it's an incredibly practical tool we use every day.
Okay, so let's zoom out for a second. We've been talking about polarization, which is a great example. But let's talk about the whole big picture. Why is really, truly getting RF propagation? Why is that the thing that separates a good RF professional from a truly great one?
Because this knowledge, it isn't academic. That's probably the most important thing to take away from this. We're not talking about stuff you memorize for a test and then forget. This is the stuff that determines whether your projects succeed or fail every single day.
I mean, just think about it. How do you decide the best place to mount an antenna? You got to understand propagation. How do you build a link budget that you can actually trust? Propagation. And when a link goes down, and you know it will, and everyone's looking at you, what's the first thing you think about? Propagation. It is the absolute foundation of our entire field.
And this quote really just says it all, doesn't it? The ionosphere is a living, breathing system driven by a star we cannot control. The RF engineer's job is to understand it well enough to work with it. That's beautiful. We can't tell the sun what to do, we can't change the laws of physics, but we can understand them. We can anticipate what they're going to do, and then we can design our systems to handle it. That's the real craft, right? The art and science of what we do.
And that right there,
That's the decisive edge. The engineer who's not just looking at their own gear, their own spectrum analyzers, but is also keeping an eye on the sun, on what the ionosphere is doing, that person is always going to have an advantage. They're going to see the bigger picture, and that's how they'll solve the problems that have everyone else scratching their heads.
So if you want to gain that edge, the RFI Detectives tutorial actually points to some essential resources. And this is so important because this stuff is always changing. It's not something you learn once and you're done. So keeping up with things like the ITU recommendations, the NOAA space weather updates, using tools like VOCAP, this is how you stay sharp. This is how you stay at the top of your game.
And you know, as we keep pushing the envelope, higher frequencies, more crowded spectrum, more complex systems, these challenges are just going to get bigger. So it kind of leaves you wondering, right? What's the next big propagation puzzle we're all going to have to solve? Definitely something to think about. Thanks for tuning in.